Okay. Hi, everybody. We will begin today our work with a specific and short discussion concerning 2 or 3 previous examples, because I want to illustrate to you some additional information regarding them. The first example is this one. As you see, this is the block diagram where we use the IMAQ region of interest profile function in order to find the area of a given configuration or image. The image which we are working with is the battery clamp. This is an interesting image indeed because it has a specific configuration, and I will use it in different programs so that we can compare the results which we obtain. When I discussed this with you in the previous lecture, I remember I told you that this is one of the most interesting functions, which is the IMAQ Edge Tool 3. Using this function with the IMAQ region of interest profile function, really, we can find a very accurate approximation of the coordinates of the contour of the image. Here at the output of this function, we get, as you see, the global rectangle coordinates, and we get also the pixel coordinates, which is an array of clusters. I can show it to you. It is an array, as you see, of clusters. And these values are X and Y coordinates of each point of the points of the contour, as you see here. The idea here is you need to find a number of edges and a sufficient number of edges to be included in this array to be used to find the area enclosed within this contour. You can do this, of course, by freehand sketching, as I did here. You look at the green line, green curve here. I had drawn it, and when I clicked the program to run, I found that the area was about 54,237 pixels. But where is the problem here? The problem is you need to be as much as close to the real edges, and you have to get a sufficient number of points so that the calculation is highly accurate. But the most important drawback here that you need to sketch freehand. Every time you need to do that by hand, this means this process is not automated. It is not graphically computed, not programmatically computed. What I have done here, I tried to carry out an experiment here to evaluate the area of this object by using a programmatically realized method. What I have done, I kept the above program as before, but or what I have done, I took the path of the image of the file, and this is the file, the image which I get there is done. Image2 is the same as image here. This image is introduced to IMAQ Overlay Multiple Lines. This function allows you to draw and overlay unlimited number of lines, IMAQ Overlay Multiple Lines 2, it is this function, unlimited number of lines connected with each other, and these lines are going to intercept with the borders of the image itself, so that to discover the edges there. So the higher the number of the lines which intercept with the contour here means that you generate a higher number of points and you are becoming closer to the real area. Where is the advantage here? The advantage here is you get the array of edge points here programmatically. Here the input is an array, this line endpoints. This is the array I have drawn. As you see, these are piecewise lines approximately done. Of course, you can make them much more closer to the edges and get more accurate results. But the advantage here is you do this once only, and for the same, of course, configuration. And of course, you can do a more generic piecewise line which intercepts with the borders of similar shapes to this shape or another shapes. You can have it in advance before running the program. So when you run the program, practically you get these points, which are the edges, and the number of these edges will be introduced to the area finding function, which means that we have find the area programmatically without drawing every time the freehand curve which intercepts with the contour of the object. So, as you see here, the advantage and the power of this function is you get edge information as clusters. This is one cluster, the second cluster, the third, and every cluster is related to a given point only, X, Y point in pixel values or in real values and other additional information. So the number here, as you see, 291 edges. If you put here, for example, number 200, you will get values. If you put, let me say, 300, we will not get it because it is more than there. 300, for example, it is empty because there is no edge with a number, serial number 300. So this is really a very powerful and very interesting 250, for example, you get values. The last value here is the value which is for the 250 point. Now, when I run the program, I found that when I enclosed the object with a very fine and very close, as you see, not linear wise, contour which intercepts, of course, with the borders, I got the value really very nice and very clear, very close to the real value, which is about 54,237. The value which I got when I approximated the multi-line drawing, it was about 57,000. Of course, I told you again, I tell you that this could be much more closer to the real value, which is here. So I think this is interesting for you. And I have written for you some advices about this, that with IMAQ region of interest profile, we can extract the pixel coordinates of the points lying on the region of interest contour line only. Here is the problem. So using freehand drawing, you can define edges coordinates of any complex irregular configuration, and as a result of that, you can define its area. You can define the area of open or not open configuration by closing it with freehand sketching, and then you will get the area of the closed. Here, as you see, this circle is not closed, but I can close it by freehand sketching, and I can find the area inside it. The higher the number of edges and the closer the drawn curve to the real borders of the object, the higher the obtained accuracy. This is which I wanted to tell you about this example, 16.1. Okay, let us go out of it, and let me also tell you something about another example, because, you know, I am trying always to improve the information which we can get. This is 16.1. I don't need it. I will need 26, maybe 1. 26.1. This was also discussed with you. We are working also with the same object here, which is the battery clamp, as you see. And you remember, we have found the area of this subject again by using IMAQ extract curves function. This is a marvelous also function. And I remember in the previous lecture, I have shown you this figure as the contour, and I have told you that the area was about 54,173, which is practically the same as that of the previous method which we did. But what we did not do here, I tried to make an approximation to find the areas of these two circles, which are inside the configuration, in order to subtract them from the total area and to find the netto value. Previously, I made this approximately by eye. I told you I have estimated the radius and found the area of this circle and the area of this circle, and they were about, as you see, 1,033 pixels. This one was, and the other one was about that value. They are very 1,020. What I did now, I introduced or developed an addition to that program The output here, as you see, is an array of clusters. This array includes the array which is related to the configuration as a whole, and you have other two arrays related to the small holes. I extracted both holes and I found the points for each of them. I have drawn each of them alone. This is one of the holes, this is the other hole. And then I found the area for the first one and the area for the second one. So as you see here, the area of the first one was 1020 pixels and the other one 1027 pixels. But this is done programmatically. There is no estimation by me here. And of course, in order to get the net to area here, you have to make the sum of both small areas and subtract them from the whole area to get the result, if this is required, of course. But what I intended to tell you that you can do this programmatically as I have shown you, and I think it deserves also to work with this and to show it to you. Okay, I leave this 26.1 and I move also to 26.2, which has been also discussed with you. Here we used this function in order to find the array of clusters which defines the coordinates of the contour. And we found the area here, and it was about, it was about 54,163. That is the same as the previous two answers. But what is new here, maybe also, I have used this function. This is the IMAQ find circular edge, number 3. So if we go to the front panel, here it is. Now, by using this function, I define the contour, and as a result of that, I can define also the area. So this is another way to calculate the area. The area of the small, the total area was, as you see, as before here. The small area, why it is too much for me, I am not sure of it. Let me try it under your eyes to be accurate. And then if I run the program, it is 880. There it was about 1020. Maybe I could be more accurate. I think this is good approximation now. If I run it, it is 1022, which is exactly very close to the result which I have got for the same circle in the previous example. So I think this gives you more confidence that what we are doing is exactly the correct, safe, and we do not have any problems with the offered programs. So you can use it in your practice. Okay, so let us move now to another new examples which we will discuss with you. we discussed at the end of the previous lecture the example number 27. It was discussed. Now we are at 28. We have 3 examples with 28. Let us begin with 28. Edge detection with Sobel. Here is, it is really a simple program, but I am including it for you because we very often use Sobel as a filter or as an edge finding method, and also with canny filter. So this is the function which reads the path where the image exists with the information with it, and we feed it to the IMAQ Edge detector. Here we select from different choices the type which we like. I wanted to show you how we work with Sobel, and the output exactly gives you the contour. Here is the output edge of the element which we are looking for. It is not difficult to go through it. You can practice it by yourself. So just I wanted to pass by it quickly to show it to you. This is 28. So if you want to see another example, let us go, for example, to our beloved method, this is a gear, for example, or a motor, a worm gear. Let's see the worm gear, for example. Now it is here. And if we run the program, this is the edge of the worm gear. If we want to go to other object, there is no problem. You can do the same. So exit. This is 28. 28.1, filter using IMAQ convolution. Okay. So we need to, this is the original image which we have. As you see here, I have added some noise on the image itself, and we want to clean it to have it without these pepper and salt noise, which is on the face and on the hair of this girl. So the program itself, as you see, begins as usual by reading the image. So here is the file path, and this is the read function, and now we have to read them. This is the image which we are going to read. But we do not read it directly from here. At first, before working further with it, we make a copy here, this function, IMAQ copy function, IMAQ copy, and is used to get the original image without any disturbance, without any effect or back effect from the filters which are used here. This is the recommended way to do it. You always have to use IMAQ copy, and then, of course, allocate a specific buffer area for the image, and this is the image which is produced. Now, this image is really the original image which we have. Okay, now we go back to the block diagram. So we have made a copy of it, and now we converted the color image. It is a colored image. I have converted the color image to a grayscale value, and it is input to the function which is IMAQ convolution function, IMAQ convolute. We have used it twice. So the image now is grayscale, and it is input to IMAQ convolute. For IMAQ convolute to work, it needs a kernel. The kernel you have to try to select the most appropriate kernel. Normally we do, but remember that it should have an odd size, 3 by 3 or 5 by 5 or 7 by 7 or 9 by 9 and so on. Here it is taken 5 by 5 double array, the two-dimensional array or matrix. And of course, if you want to know about it, I can show you that this is merely a filter. IMAQ Convolute VI filters an image using a linear filter. So here is the input, which I have connected with. And this is the destination where we need to allocate the output if it is required. And this connection here is the kernel which I have created. So this is the kernel, and here it is connected from here. We have connected two kernels with these numbers, which are appropriate for this task. And as you see, the output now of the two filters is fed to a thresholding function. This is a threshold function, IMAQ threshold, which converts the filtered grayscale image to a thresholded image. And these are the lower and the upper thresholding values. Here just I have wanted to show you at this stage, after the first filter, and at this stage after the second filter, how the image is changing. If you go back, it is called convolution 1, and this is called convolution 2. If you go back here, you can see both of them. This is the first one, convolution 1. This is the image now grayscale, and this is the other one. Also, it is a grayscale. Now, after it is thresholded, it is really fed to a function which will work with the noise which I have introduced. IMAQ remove particles. Here you have the number of iterations which you can find the most appropriate. You have to select 1, 2, 3, 4 to get the best value. I have got an acceptable value really with the first iteration. And so at the output here now, I have to get the image which is clean without any pepper or salt. Look, here is the face which you have seen there with removed. And here also is another image for the face with removed particles and cleaned face of the girl. What is there left? Here I have introduced a time delay, by the way, in order to fix the image on the display for 20 seconds. And here also I have managed to see the image here, or to look at the image with the required background, red or blue. Here F00, FF red. If you put here another FF, you will get a white image. Here FF, and if you run the program, you have got a white image here. If you want it to be red, you have to, let me stop it first. You have to put it as red, which is FF, 00 for the green, 00 for the blue, and then it will become red. I think it's okay. How it works, it is not that difficult. Here you have a selector switch with a logic input. If the logic input is 0, it is not 0 always. It will have a value as usually here, or black. We do not need black. We need a value from here. So if this is not 0, this function, which is false, will work and give you the output, which is the final value which we get. So why I am giving you this information? It is necessary. Everyone who works with images needs always to clean the images from external noise and disturbances. And this is one of the ways to do that. Of course, the field of filters is very large, and really you can work on it as much as you want and spend the required time. So 28.1 filters using IMAQ Convolution, now we know it. 28.2 remove particles, it is the same, really, I gave it different name only. Let us move to 29. Extract edge image using convolution. So here we are using convolution filters as we use Sobel, for example, filter, in order to get the edges of the image. So here is our target. So what do we have? We have an image located in the memory through this given path. It is JPEG type, so I read it by JPEG read function. And now this, as you see here, the array is already one-dimensional, and I get here the data of the image. I can, it is already written, draw flattened pixel map, and the new picture here shows you the picture or the image which is there. This is the picture which is the image of the battery bracket. Okay. Now, I took this data and unflatten the information, which means I convert the one-dimensional array to a two-dimensional array. And as you see here, we have 2 lines, which means two-dimensional array. And this two-dimensional array now is divided by the maximum value of the values in the array itself and multiplied by 255 to get an image value. This is the image value which I got it here. It is exactly the same as here. This is the same as here. Now, I work with this image value. It is the input to a convolution virtual instrument, VI virtual instrument. It is the input to the convolution VI, and practically it is going to be multiplied by this kernel. It is a filter called Laplacian type 2. It could be Laplacian type 1 or Laplacian type 2. This is, you have the choice, Laplacian type 1 or Laplacian type 2. So you select whatever you want. Maybe there is different results for you. And the output now is taken as an absolute value, converted to an image. And this image now is inversed to get the output. This is the edge of the figure. Maybe you see why. This is the input bracket. Yes, here the input is bracket. If I run it, it will be a bracket, of course. Here it is. So the frequency is small. The time of delay is small. Now it is okay. So this is the edge which we have got as a result of convolution of the image with the kernel. The convolution function, this convolution function, is not IMAQ or vision function. It is really LabVIEW function. It is a mathematical function. You go to the basic palette here to, let me say, signal processing, and you go to the, I think you go to the filters, if there are filters, is there, this is the filters. No, not found here. Let me try again. So we are here, we go to the mathematics maybe. No, it should be with the signal processing or measurements. Signal processing, there should be something related to filtering. Filters. Yes, filters. Here is advanced FIR. When you go to the advanced FIR, you find here the convolution function in the subpalette here. The convolution function. This is the convolution function, which is here. So, as shown there, it is a multiplication of two matrices. One of them is X and one of them is Y. This is the convolution. So this kernel represents X and the image matrix represents the Y. They are convoluted together. As a result of that, we get this absolute value of the product of them, which represents an image. The function here, and here just to allocate memory for the images. Now the output of the image is here. What I have tried to make, maybe I have forgotten. Let us try, please, because I do not remember all the detail here. Let me open it. What is there? Okay, here is the image. No, it seems to me I didn't do anything. I was trying to do something, maybe. Okay, so here the image, I took the image as an input to the XY to find its contour. Really, I found the contour points as an array here. And if I open this array, here it is. If I run it, is there anything? No. So this was a trial done by me, but I have stopped trying there to do anything with it. I can now cancel it so that not to be used by you. So all this part is not necessary for you, and we can keep the rest, which represents how to generate a contour or edge of an image by using convolution. Let us go back to see. Yes. Here it is. Okay. Next example. Save. Example number 30. Extract edge image using convolution. Is there any difference? I did it, I think. It is this one which I have done. Extract external contours using IMAQ function or IMAQ. Okay, let us try to see 31. This is also a simple example. So as you see, this is also an external contour of a piece of equipment, and we are trying to find it programmatically by using two ways. One of them is IMAQ Edge detection. This is the function. We have passed it. We have seen it before. And this is the IMAQ convolute, which I have shown you before. So this will give you a contour at the output or edge output, and this will give you the same result here. So if you run both programs, of course, you will get the same result. Of course, you can change. Let us try to change, for example, this is classification. Let us try motor, for example, in classification. This is the motor, I think. No, the image is not large enough. It is not sufficient for it, as seen from here. No problem. Okay. Example 32, use of IMAQ Get Points on contours. Yeah. This is our function of interest. IMAQ Get Points on contour. I am trying here to make use of this function to define the XY coordinates of the contour of a given image. The image which we are working with is the same battery bracket. Here is the points which I have got as a result of applying this function. As you see, the number of segments here is 1055 segments, which I have got. Of course, the higher the number of segments, the approximation is closer to real. This depends, of course, on the thresholding value here, because the input image must be thresholded before it is fed to the IMAQ Get Points contour. This is the disadvantage, maybe, of this function. But it works well. So I have thresholded the image, which is coming from here, and the thresholding values are the best values I have obtained were 241.1, 249.3. If I put now it is 128, of course, this is not good. So I have to move it. I have made a digital display here to be more accurate. 241. This is 200. Okay, very near. And this is 249. So it should be okay, like this. Now, if I run the program, I have got the answer that the area is 54,180. Remember that all the answers which I have got through the last three examples using the same battery clamp was about 54,000, which means very accurate result. The number of segments now is 1,150. And here you get at the output really, as you see, this is an array of clusters, and each cluster is specific for each segment, which for each segment, you have the number of points there. And if it is open or closed, and the contour points coordinates. If you go to the block diagram here is our function, and here is the output where the segment information I am talking about. So you need always to work with segment information and manipulate it in a given way so that you get as the output the coordinates of the contour, which could be used by the find area. This is why it doesn't give. It is running because it is running. It is called IMAQ find or polygon area function. So I think now the usage of the get points contour on a contour or of a contour is now well understood also, and its application here illustrates for you this example, which I think is sufficient for the time being. Find number and show location of edges and their XY coordinates. This is interesting, but I think it is not difficult for you now. But it is very interesting also. So if you go to the block diagram here, sorry, this is already, we have finished with it. Don't save, why not? So as you see, we are working with IMAQ select line and IMAQ get points on the line. We can get points on a line or get points on another curve. Yes. Here at the output, we shall have an image. But on this image, when we draw a given line, this line will intercept with the edges of the image. And the coordinates of these points will be given. So, as you see here, this is one edge, which is an interception. The line is going this way. The coordinates of the line may be drawn, as you see here, for example. I can draw it. And now I have one edge, two edges, three edges, four edges. If I say OK, I will have another picture now, which represents the edges, the new four. To be clear, again, if you go back, let me draw it differently. No, I have to run it first. Let me draw it, for example, through these two circles like this. So we are having, as you see, 0, 2, 3, 4. If I say OK now, and we go there, we shall find this is one edge here, the second edge, the third edge, the fourth edge, the fifth, and the sixth. So we have here, we should have here 1, 2, 3, 4, 5, and if I expand it, we shall have the 6 coordinates. But if I expand it more, it will have nothing. It will not give anything. Okay, so I think with these examples, you have to work on them on your own. Try to draw it by yourself, to modify according to your need. And I hope that this will be very useful for you. And until next lecture, I hope you a nice and a happy day, and good luck for you. Safe.